Hey everyone, I am Álvaro Ramos from Universidade Federal do Rio Grande do Sul, and today I'm gonna talk about totally umbilic surfaces in hyperbolic trimanifolds of finite volume. And this is a joint work with Colin Adams and William Mix, and I would like to thank the organizers for letting me give this talk. So, first of all, let me try to explain a little bit about the title of my talk. What is a hyperbolic trimanifold of finite volume? A hyperbolic trimanifold of finite volume is, well, a hyperbolic manifold, which means has constant curvature -1 and which has finite volume. So, okay, that doesn't help much. How do they like, and do they even exist? So, in fact, until the work of Thurston, we didn't know many examples of hyperbolic trimanifolds of finite volume which were non-compact. We have closed hyperbolic trimanifolds which have finite volume because they are closed, but non-compact examples, which is more or less the focus of my talk, we didn't know much. But the picture today has changed like by a lot because of the hyperbolization theorem mainly, which is, here's the statement, I'm not going into it, but it gives you a reasonable way of finding out if your manifold admits a hyperbolic metric of finite volume. This theorem was proven by Thurston and improved by Perelman when he proved geometrization and the Poincare conjecture. Okay, so the example to keep in mind, and this was a lot of what Thurston did, was the complements of knots and links. So let P be a closed trim manifold and take a link in this manifold P. So what is a link? A link is something which is several S1s embedded in your manifold, which can be linked or not. Maybe they are not linked by the definition of the word link. So a knot is just an embedding of S1 inside a space, and a link is several knots which are disjoint. So we say that a link is hyperbolic if the complement of the link in your manifold is hyperbolic and admits a metric of a hyperbolic metric of finite volume. So here are a few known examples, and I took these pictures from the Thurston's book. So we have here Borromean rings, the daisy chain, the figure 8 knot, the Whitehead link, twisted daisy chain, this other thing here which is called the E5 link. It's really messy, but all of these have complements in S3 which has a hyperbolic metric of finite volume. So let me show you how to see, at least how do I see a hyperbolic trimanifold of finite volume, which is a knot or a link complement. Take your knot here, this is the figure 8 knot, but represented a little differently, but it's the same as I showed you before. And you take this in S3 or in your other manifold, any hyperbolic link. And what is your hyperbolic manifold? Is everything but this knot or this link. So it's the complement of it. So let me explain what this means. You take a neighborhood of your link or knot, and this neighborhood has the following topology. Here in the core we have a S1 curve, and here you have another S1 curve, and you have a foliation by this S1 curves. So the topology of the boundary is the topology of S1 times S1, which is just the 2 torus. Now you do this for each component of your link. And then you have this neighborhood here, which is just the torus times 0, 1. And when you are 0, 1 open set, then you can actually think of this as going to infinity. 0, 1 is diffeomorphic to 0, infinity, and that's what it is. You have these ends of your manifold, and going to this core curve means going to infinity. So the way of seeing a hyperbolic trimanifold of finite volume is something like this. You have ends, and all these ends are ways of going to infinity, and they are really thin. They start to get really quickly, very smashed together, so they have finite volume here in the end. And here you have this thick part. The thick part will be the complement of this solid tori regions, okay? And then what is more impressive, what is the best thing about these manifolds, is that we can understand this cusp ends. They are called cusp ends. I think I didn't say it yet. And they have this topology of a torus T2 times 0 infinity, and they start to shrink really rapidly, so you have finite volume when you measure the volume of this region. So this is very interesting because all these ends are actually quotients of a horoball. You go to hyperbolic space H3 and I like the half space model. So here a horoball is just everything above some plane z equals a constant, and these horospheres here, which are z equal another constant larger than this one, go to this tori. So all these tori have constant mean curvature 1 and they are intrinsically flat. So that's the picture of the ends of a hyperbolic tree manifold of finite volume, and what's left, it's just something hyperbolic with toroidal boundary and, well, compact. Okay, so now that we know the ambient space we are working with, let me show you some motivation to our results and the statements of our results. So first, let M be a complete hyperbolic tree manifold of finite volume, and let sigma be a surface of finite topology which is two-sided and properly immersed. Let me just recall what finite topology means here for surfaces. A surface has finite topology if it is a closed surface of genus G. Let's think that everything is orientable during the talk, okay? I forgot to mention that. All the results here also work for non-orientable, but I will focus on the orientable case. So a surface has finite topology if it is a closed surface with genus G and a finite number of points removed. So these points are like the ways of going to infinity on the surface, okay? So you take this hyperbolic manifold of finite volume and you take a surface of finite topology which is two-sided, think orientable, and properly immersed in N. So the first theorem which motivated me to study hyperbolic tree manifolds of finite volume is this theorem by Pascal Colin, Lohan Halsworth, and Harold Rosenberg in 2015, which says that if sigma is a minimal surface in N, then each end, and it's properly immersed, never forget that everything here is properly immersed, then each end of sigma is asymptotic to a standard totally geodesic annulus in one of the cusp ends of sigma, and moreover sigma has finite total curvature equals to 2 pi times its Euler characteristic. And now I'm thinking of non-compact stuff, so this could not be true, right? So this is a beautiful theorem. They actually do a little more than that. They also work in another space, which is the product of a hyperbolic surface with S1, so a manifold covered by H2 cross R. But here I am interested in this statement. So a few years later, Mix and I, we generalized this result for CMC surfaces in this range, 0, 1 for values of 0, 1, and we find the same thing. Each end of sigma is asymptotic to a standard totally umbilic, because now mean curvature could be positive, so it's no longer totally geodesic, and totally umbilic annulus in a cusp end of N, and it has finite total curvature equals to 2 pi times its Euler characteristic. So in both cases, we know that this has to be negative. The curvature of sigma, the intrinsic curvature of sigma, has to be negative. So the Euler characteristic of sigma has to be negative. In particular, there are no spheres, tori, planes, and cylinders which are properly immersed in a hyperbolic tree manifold of finite volume with mean curvature, with constant mean curvature in this range between 0 and 1. And well, this gives some questioning, this raises some questioning. For instance, what about other topologies? What about other values of age? And in our situation, more importantly, do the surfaces exist? Like, we have this theorem, we would like to know that it's not empty. The minimal case, we know that it's not empty, but for other values of age, we are not sure if it's empty or not. So this was the question: what are the values of age and the topological types that can appear as properly immersed or maybe properly embedded surfaces of constant mean curvature age in some hyperbolic trimanifold of finite volume? This was the first question we asked to understand if our theorem was empty or not. And actually, the minimal case, as I said, it was already known by these theorems by Hess, Rubinstein, and Wang, and Coulomb, Hauswirth, Mazet, and Rosenberg, which gives a very reasonable way of finding least area embedded minimal surfaces in hyperbolic trimanifolds of finite volume. So since it's least area, is the minimal case. And here is the answer we found for the existence theorem in the more general setting. So this theorem is what I'm going to show you today. Is the existence theorem, is by Adams, Mix, and myself. So take your value of age, your favorite value of age in this range 0, 1, and your favorite surface S, which is admissible in the sense that it has finite topology and negative Euler characteristic. Then we can find a complete embedding of sigma, of S, into a hyperbolic trimanifold of finite volume with that constant mean curvature. So this theorem actually says anything that could exist actually exists. And that's something we were really relieved, because we didn't know if those surfaces actually existed. But there is something else. We don't just find them with constant mean curvature, we also find them as totally umbilic surfaces. So that's the title of the talk, totally umbilic surfaces in hyperbolic trimanifolds. But moreover, this is just the existence theorem. We also have a characterization theorem, which I will not go into the details of its proof today, but it goes more or less like this. If you have an embedded, so I'm not assuming proper, and totally umbilic surface with mean curvature h non-negative in some hyperbolic free manifold of finite volume, then the first thing is it is proper. We don't have to assume properness if you have embeddedness. That's something as a Calabi-Yau problem for totally umbilic surfaces in hyperbolic trimanifolds of finite volume. So it's proper, and moreover we can kind of classify everything that can happen. The Euler characteristic is positive if and only if it's a geodesic sphere and the mean curvature is bigger than 1. The Euler characteristic is 0 if and only if n is non-compact, so it's a non-compact hyperbolic trimanifold of finite volume, and the mean curvature equals 1. So in this case, sigma is one of that tori in the cusp ends of your manifold. It could be also a Klein-Bottle in the non-reanable case, but I'm not going into that. And finally, if the Euler characteristic is negative, if and only if the mean curvature is in the range we wanted it to be, in between 0 and 1. So that's a subject for another day. Today I will focus on the existence theorem, and right now I'm giving you the outline of the proof so that you keep in mind. It's going to be a long proof, and I want you to keep in mind the ideas of what we are going to do. So the proof goes more or less like this. You fix your value of h and your surface S. So this is just a topological surface so far, and the first thing we do is to go for the totally geodesic example. First, we find a totally geodesic example in some hyperbolic trimanifold of finite volume. This would be more or less proving the h equals 0 case. Then, oh sorry, and this is going to be in the next video, which is basically a topology video. It's more focused on topology. So then after that, we have this totally geodesic example, and we can use it to construct examples which are totally umbilic with larger mean curvature. We do it by looking at the t-parallel surfaces to sigma, which is just go parallel. You take the exponential map and you go a fixed distance. This will be done in the third and last video of the talk, which will be more a geometric video. So the thing about the t-parallel surfaces is that any t-parallel surface has constant mean curvature equals hyperbolic tangent of the distance you went, and this is always a number in 0, 1, and when t goes to infinity, this number goes to 1. So you can actually find constant mean curvature with any range between 0 and 1, but you still don't have all the other nice properties. So you need to prove that every one of these t-parallel surfaces is properly immersed, and you also prove that for small values of t, these surfaces are properly embedded for all t less than this constant. So for small values of h, we already have the theorem. And the third and last part of the talk will be to reach any value of h that you want. And the idea to do that, you find the t naught that you want to be embedded, and you assume that you cannot go that far, but then you construct a finite cover of your manifold so that the totally geodesic surface lifts, and the parallel surface, when you go that distance, is still properly embedded. And that's the outline of the proof of this theorem, and we will continue next.